Hi everyone, I hope that you're doing well. In this lecture, I want to introduce you to some basic descriptive statistics and also the concept of inferential statistics as it pertains to the social sciences. So we're going to start with some basic operations that you can do really just as a way to describe a data set. These don't need to necessarily say anything about the larger population. These are the types of things that you probably learned at a very basic level in grade school and then probably spent a little bit of time, although probably not much, on in high school if you went to high school in the United States. If you went elsewhere, I can't really comment. What we'll learn is basically just these kind of simple ways of characterizing data. And like I mentioned before, these descriptive statistics, as they're called, won't necessarily have much theory to them. They're, for instance, the sample mean, ways that you can characterize sets of data that don't require too much theory. But then we'll discuss the logic of inference, which tells us basically whether or not these things generalize to the population, and if so, how we might go about doing that. So let's start with some basic operations. So suppose you run across an expression such as this one here. I won't pronounce it out loud because that would sort of spoil the surprise. So I just want you to look at this and see if you have a sense of how you might evaluate this. So this is the summation operator, sigma here. And what this tells you to do is it tells you to sum over all of the individuals that you observe on some outcome y, and to sum up from the first individual to the nth individual. So really what this does is, all this tells you to do is take the total or the sum of a variable that you have in your data set. Most of the time, this will, for our purposes, involve summing from the first person to the last person here. But there are other situations in which that's not the case. I'll show one next week where we talk a little bit about ANOVA, and we'll see that sometimes we're summing not over individuals but groups. But here, for the meantime, we're going to sum over individuals. And I want you to note a couple of possibly tricky bits of business here. So this I is not really a variable, it's an index, and it basically just says, it kind of keeps track of different individuals. So what this is useful for is making sure that we're clear what set of people we're summing over, basically. Now, someone's index number is not actually typically an important part of a data set, and many times when you're doing data analysis, you'll need to resort the individuals so that in the software that you're using, for instance, the person who came first initially is not the same person as the individual who came first when you first got the data set. There are some data sets that include ID numbers so that that number will stay constant, but other data sets don't, and then the ID number is just implicitly the row that they're in. So resorting the data, as long as you sort, all the columns, and most software won't let you just sort one column and not change anything else, that type of resorting operation is totally fine to do for most purposes, and there's really no importance for virtually all descriptive statistics except for those that involve quantiles, which we won't discuss in this class. That's stuff like the median and so on. So you don't really need to worry too much about who individual 1 is and who individual n is. Basically, this is just telling us keep the individuals separate and then sum over all of those individuals. Note, by the way, that n here, this little n, is a constant that means sample size. So this is not any kind of a variable. I know that can be somewhat confusing, but n will typically be held to be the sample size. We've also got this yi here. So what does this mean? So the y is a variable, or more properly, it's a realization of a random variable. So we'll learn in just a moment that random variables, and I've already expressed this if you're in my SOC257 course, are typically denoted with capital Roman letters. Roman letters are the ones that we use in English. Smaller case or lowercase Roman letters are basically realizations of those random variables. So here, this little y basically means that this is a observation on the random variable y. So let's say y, capital Y, is income. It's just the abstract concept of income, or the slightly more concrete concept of income in some population. But then little y basically represents some actual sample income. And that's kind of vague because what does that really mean? Like just sample income generally. So typically we mean a specific observation on it, and that's what this notation here means. So y sub I means basically individual i's income. So this is still pretty abstract. It's kind of funny when you really think about it. We are abstractly denoting something very concrete. We're abstractly denoting the concept of a specific individual observation on whatever variable y is. So I know this is kind of funny because we're talking very abstractly about something that actually isn't that abstract, but that's sort of how statistics work. So what this tells us to do is for any actual concrete set of data we have, just sum everyone up. That's a pretty easy thing to do that you could have, you can write that in much simpler ways, but there's a reason to write things in this mathematically consistent way, which is that it's concise and it allows the development of a coherent science about these things. Okay, so enough said about all of that for the moment. Let's go ahead and see how we might put this into practice. So here I put up a simple data set, and by the way, this is a textbook effectively that I wrote. We've got the simple example data set here. We've got individuals 1, 2, 3, and 4, and I want you to try to carry out the arithmetic operation indicated by this notation here. So you may want to pause the video at this point and make sure that you can do that. This won't be a useful thing to do by hand too often, but it's good to try it once. So try to pause the video here if you want, and then we'll pick back up. So welcome back if you pause the video. Hopefully you saw that the answer is relatively straightforward here. We're going to obey the sigma notation here, which tells us to start with individual 1. And again, the order, as you can see, doesn't really matter because summation is commutative, for instance. So the order of the items summed or the summands doesn't matter, as mentioned before. That's true for almost every operation we'll do. And so we start with individual 1, but we could just pick any old person. And then we simply look at y for that individual, 3. And then we add that to the y for individual 2, which is 10. Then add that to 2 and so on, and then to 4.5. And you can see that the answer, you can click on these footnotes to get answers, is 19.5 here. And click on the footnote to return to the text. So the answer is 19.5 there. So that's our first basic operation. And I know this notation can seem a little bit scary, but that's really all that it means. And sigma, by the way, is a capital Greek S, so it makes the S sound. And we'll later on meet the lowercase Greek s, also sigma. It looks a little bit more like an O, somewhat confusingly. But Greek letters typically have intuitive meanings, so they make this sound, although I know that's maybe not intuitive if you don't know the Greek alphabet, but there is a logic to it, and the people that came up with these things were educated back in the day where Western Europeans and Americans all had to learn Greek and Latin. So just for the record, so that you don't feel totally kind of resentful towards these people, at that point these were very intuitive things for people to do. They were like, we want to keep the Roman letters for random variables, so how do we indicate these operations? We'll use the Greek letters. So there we go. Okay, so now let's define the sample total, which is our first kind of experience with a little bit of estimation. We're not actually going to do much of the sample total in the inferential part of the class today, but I do want to just introduce you to some of the problems that can arise when you try to move from the sample to the population. And you may wonder, why do we want the total? And that's actually a pretty good question. Typically, the total in itself isn't that useful, but it allows us to get started with some tricky bits of business, and simultaneously, it also lets us see that sometimes it is useful to do even this very simple operation here, just sum everyone up and see what you get. So let's imagine that we want to estimate the population total, maybe the population total income. That might actually be kind of interesting because the total income, in theory, should be the same thing more or less as the total GDP. I mean, there's actually a slight difference there. Maybe you could think about it, as being a way of comparing it to the GDP, because it's actually somewhat of a separate concept. So anyways, it's comparable to GDP. One is the output produced in the US, the other is the income received, and maybe you want to compare the two. Okay, so first you might notice that we need to actually work a little bit here with sample weights. And that's not going to be a big part of this class, but remember that we have discussed sample weights a little bit, and now I want to show you what that looks like in practice. So why would it be foolhardy to just sum up the sample total and then use that to estimate the population total? Well, the sample is much smaller than the population, and so here we need to adjust for the size of the sample. That won't be true for other things we do. So for instance, the sample mean does not actually depend on the size of the sample, or at least I should make that a little bit clearer. It auto adjust for the size of the sample. There's still other reasons that the size of the sample can affect the mean, but they're indirect. It's not necessarily going to produce a biased estimate. Whereas if we just take the sample total and then use that to estimate the population total, that will be biased because we know that it'll systematically undershoot. Okay, so how do we use these weights? What are these kind of scary looking weights? Well, I want to mention a couple of things here. So first, our weights are simply the inverse probability of selection into the sample. So all we need to do is just figure out what probability individuals in the sample had of getting into the sample and then multiply by the inverse of that to undo that problem with size. Note that this gets really tricky when observations have different probabilities, but if they don't, it's much simpler, and I'll show you the math in a moment. And I want to mention this last bit of kind of notational throat clearing. I've already mentioned this once before, but just to reiterate. So in general, when you see letters used in math, in statistics specifically, Greek letters mean things like parameters. These are facts about the population that we want to know but can't directly observe, such as the population mean or the population standard deviation. Here, this thing that looks a little bit like pi, which is probably more familiar to you, but it's not. This is tau. It makes a T sound, and this stands in for the population total. We've got some other types of letters to worry about, though, as well. So we've also got capital Roman letters. Those are random variables in their most abstract form. So what that means is this is something like the concept of income or the concept of education. It's a property. It's not something that really has a direct mathematical expression. It's more conceptual. So if I think about something like, for instance, we saw this before with capital Y bar, that was the sample mean. That's the concept of a sample mean, but it's not a specific sample mean. It's not even the abstract concept of a specific sample mean. It's just the pure concept. So when we do want to refer to the concept of something specific, I know that sounds kind of wacky, but just keep in mind, and there's a lot of good philosophy about this actually, but keep in mind that you can have an abstract concept of something specific or an abstract concept of something fairly abstract. So when we see lowercase Roman letters such as little y, that means the abstract concept of something specific, like an actual observation on a variable. So it's the concept of a particular person's income or education. Okay, finally, I wanted to mention one more thing about notation here. You'll sometimes see pi in this context, and here pi, again, the sound that the letter makes in Greek is informative, makes the P sound. So this here doesn't actually mean Archimedes constant, 3.1415926, etc. It actually just means probability. So how would we read this notation here? What is this telling us? One more thing I meant to mention. So these carets or these hats mean sample estimates. So what this is telling us is that the sample estimate of the population total, subscripts just tell you like what this refers to. So this is the population total of Y, is equal to basically the sum of Y in the sample, but then multiply it by 1 over the probability of selection into the sample. And we do that because this sample total is going to be too small. So we need to multiply it by 1 over the probability that people got in there. This, by the way, is the sample size. This pi is sample size over population size. So really, because it's in the denominator, what this is population size over sample size. In other words, we basically multiply by something typically pretty close to the population size, except adjusting for the sample size. So we're scaling up the sample total to make it a good estimator of the population total. Okay, so that's an introduction to how some of all of this works, some of our notation, some basic stuff about summations and estimation, and that's pretty much it. So let's keep moving right along. Let's move ahead to the mean, which is a measure of central tendency, or something like the characteristic value of a distribution, which the mean, median, and mode all get at. So we focused attention on the mean in this class, but that said, there are some other measures of central tendency, such as the median, which are important. Medians are more robust to outliers vis-a-vis means, but medians are hard to do inference on, and there's a couple of reasons for that I don't want to get into here. But let's say that it's harder to make an inference about the population median than it is to make an inference about the population mean, and so that's one reason that we like the mean. The mean, by the way, is simply the formal term in the sample for the arithmetic average. So if you take a sample mean from a simple random sample, let's just take the simplest case, that means the arithmetic average. So total everything up and then divide by the sample size. We will talk in a second about means at the population level where they're related but distinct. We're going to focus here on the simple case where our possible outcomes of the variable are discrete, which means that they're finite in number or countably infinite. I'll explain that in a moment. Simple descriptive statistics for any real-world data set can be calculated with these simpler discrete formulae, but sometimes we will need to discuss variables with infinite possible values, which are called continuous variables. So let's discuss that a little bit further. If we record the number of cars that someone has, well, they could, in theory, tell us that they have any number of cars up to infinity, or possibly -1, although that doesn't really make any sense, but this would still work if you had -1. This is countably infinite. So setting aside the formal definition, which gets kind of heady, I hope that you'll be able to understand this part. What this means is that if I pick an arbitrary number of functioning cars that someone owns, let's say 5 cars, I can tell you the next value in the set of possible outcomes with no ambiguity. That next outcome will be 6 cars. It's not 5.5, it's not 7, it's not pi, it's not 5.2, it's 6. So cars owned is a discrete variable. But by contrast, if I ask someone about their height, okay, and they say 74 inches, I can't say what height is next, quote unquote. So I could, for example, say 75 inches, but since 74 inches is about 188 centimeters, what if someone's 189 centimeters? Well, that's closer than 75 inches, so 75 inches can't be the next valid value in the set. It's got to be something else. And you could say the same thing about centimeters. So, well, maybe 189 centimeters is the next value in the set, but what if I measure it in millimeters? And you could go up to the micron, really. And you could go even further than that once technology advances. I mean, I know people can measure stuff basically smaller than that, but even still, the point is you can always measure smaller and smaller. And so since height can take on this uncountable number of possible values, it's continuous. It's fun, although not super important, to wonder about why some variables are continuous and others are discrete. In the cars case, it's just definitional. So while parts of cars exist, if I'm only asking people about complete functioning cars, then you just don't have halves of that, right? You can have a car that's in pretty good shape, but it's missing its left or its right half, or it's got half the parts or something, but that to most people just doesn't mean functioning, so that doesn't work. Conversely, there's not really a similar limit on height though, so I can't force the same imposition on height. Okay, so that's a basic description of discrete versus continuous variables. We'll see how that plays out for means in just a moment. So the mean, by the way, is sometimes referred to as the expected value or the expectation. And when we think about means on the population level, it's no longer a simple arithmetic average because we don't really have a sample size on the population level. Sometimes we do have finite populations where there are a fixed number of people, or there is a fixed number of people, pardon me. But there are other times where that's not the case. And so then we need to think about how we actually define the mean at the population level. So let's look at this notation here. I know this is a little scary looking, but I'm going to explain what all of this means. What this tells us is that the expected value of a random variable y is equal to, and here, note that we're actually using new notation for the indices on the summation. So when you see this k here, k typically refers to something other in statistics than individual people. Typically refers to a number of variables or a number of outcomes, just some number that's not a number of people. And here, it does in fact mean the number of possible outcomes. And I used little k to be the index and big K to be the number of outcomes. You could use other formulae. Basically what this tells us here is that to get the expectation of y on the population level, we find the summation for all possible values of the outcome of the value of the outcome times the probability of it occurring. And this times the probability of it occurring is very much like the sample size that we see in the discrete formula, which I'll describe in a moment, but you probably have an image in your head already. You just take the total and divide by n. This is the part that's kind of akin to dividing like n. In the simple sample size formula, we don't worry about counting repeated values. We just count them twice, but we don't do anything special with them. But on the population level, if we know that we're going to see some values more often than others, like let's say that you have a die that you happen to know is unfair, and let's say that you happen to know that some of the probability of, say, rolling a 4 is actually assigned to a 5. So maybe rolling a 5, let's say you have a I don't know, let's say you just happen to have a 2 in 6 or 1 in 3 chance, and let's say that the probability of the 4 just happens to be 0. It's some kind of trick die. Well, then how would you calculate the expected value of the die if you wanted to gamble with it, right? How could you adjust for that fact? Well, you don't really have a concept here of a sample size. You do have a number of outcomes, but what you really want to do is sort of think about it not so much as a sample size, because these aren't really samples, and you don't actually, like, any actual sample is not going to have the exact probabilities, most likely, of the outcomes of the die roll. So what you want to do is think about, if I can, abstractly consider the probability of, say, the 5 being 1 in 3, that's basically like having a sample where the probability is exact and you just multiply by the number of outcomes, or you add up all the repeated outcomes. So for any given set of data, the formula doesn't really change, even if the variable is itself continuous. This is because all actual observed data sets are discrete. There's a finite number of observed values, so even if the variable is in principle capable of taking on any number of outcomes, even those that are so infinite we can't count them or put them into correspondence with countable numbers, any actual set of data is discrete. So if we have any repeated values, we effectively just use this as a sample estimate of the probability of observing that value at the population level. So if the variable conversely has many possible outcomes and no values repeat themselves exactly, then the estimated probability of each value is just 1 over n. And we just have the, in practice, simpler formula for the mean, which is this here. So I'm going to note one exception for our notation rules mentioned above. It would make most sense using that rule about carets or hats to denote this sample mean with mu, which we learned in an earlier class is how we write the population mean, mu, with a hat here, and then write mu y. But almost all textbooks, although not all of them, use this notation capital Y bar for the random variable sample mean, and Y bar with a lowercase y for some specific sample mean. The problem is that this notation actually breaks the general rule that we established before about Greek and Roman letters, but it's extremely common, so we're going to use it. So for any specific sample mean, Y bar, or the sample mean, is equal to the sum of the yi's over 1 over n. So basically what this does is it calculates the probability of observing that particular value, and then if you have repeated values, you get an estimate of the probability of, say, observing a 10. But you can just turn this into the simpler, older formula, and sorry, that's an extra asterisk there, so just ignore that. The simpler, older formula that you might have learned, which is this one right here. So this says that the sample mean is equal to the sum of all the observations over n. It's kind of interesting to note that you could treat this as, in one sense, this formula up here is an attempt to estimate the probability of a particular outcome, and then you're using, in effect, this formula up here. You're finding the probability of a particular outcome and then summing over all possible outcomes. If you have repeated outcomes, so you have 10 multiple times, then you would have, say, a couple of 10s here, and let's say you have, 50 observations, so you would have, in this case, 1 over n times 10, and then you would add it again, so you would have, and 1 over n would be 1 over 50, so you'd have 1 over 50 times 10 plus 1 over 50 times 10, and that ends up being 2 times 1 over 50 times 10, or 2 over 50 times 10, so it's an estimate of the probability. We would say in this case there's 2% chance you'd observe a 10, but if all of that is a little bit too much, you can just think about it as this sample formula here. So we're just summing up all the values and then taking the mean. That's another perspective on the mean that's really a whole other one, which is that you can think about the mean as being basically what would happen if you totaled up a variable and then gave everyone an equal share. That's another way to think about what the mean is. You can also think about the mean as the balancing point of a density curve. We'll see that a little bit later on as well. So there's a lot of different ways to think about the mean. That's the big point. And all you need to do is, in practice, be able to calculate it using computer software or using hand calculation when needed. Okay, So let's move on. And by the way, just keep in mind this fact about mu here. I should have made that point a little bit more clearly. Mu refers to the population mean. We've seen that before in this class, but I just wanted to reiterate that. So let's talk a little bit again about sample weights. So note that this formula here implicitly takes the inclusion of each member of the sample to have been equally probable. But that's not true with stratified random samples. And again, we're not going to use these a ton in our class, but I do want you to get a little bit used to these. So we fix this fact by multiplying by the inverse, again, of the probability of inclusion. And I'll now tell you that this is formally known as a sample weight, W. And W is just 1 over pi I, as I mentioned before. So pi I is individual i's probability of being included. Note that this is a parameter, by the way. It's not a statistic, so every member of our sample has a known probability of inclusion. If we sampled at random, it's just little n over big N, or the sample size over the population size. And if we use some other metric, it's whatever that metric gave us. So let's see how that works in the case where we do have simple random sampling, and verify that in that scenario where we do have stratified or a simple random sampling, our weighted mean actually works. This is how we write the sample mean when we do know that we have sample weights. So this is the first expression here. Let's break down what it says. It says that the sample mean little y bar can be calculated as follows for any particular sample. We take the basically weighted sum that we saw before, and you could replace this 1 over pi I with W if you want, but I wrote it here so that it's clear what it means. And we basically multiply each person's weight by their score, or their value on the variable. We sum up, and then we divide by the actual population size, N, big N here. So we need to have some sense of how big our population is. And in this case, note that pi I is just little n over big N, because in this case we're assuming simple random sampling. So 1 over little n over big N is the same thing as big N over little n. If you feel a little rusty on that, definitely review some of those basic arithmetic rules. I'll just try to give a brief explanation of why. If you imagine this as being 1 over little n over big N, and then imagine that you multiply both top and bottom by, say, big N, the big N would go out of the denominator and end up in the numerator. So anytime you have a denominator of a denominator, for that reason, it's really in the numerator, so to speak. Okay, now this is a constant, and as mentioned before, constants factor out of sums. So if you multiply every value in the data set by some constant, the summation operator is linear, which means that we can just do the summation and then multiply everything by it. It's kind of like saying, if you imagine adding up 5 people's scores, then multiply them by 5, you could just envision, say, having 5 times, and then in parentheses the summation. You could multiply through and get 5 times each person's score and then sum, but you might as well just sum and then multiply by 5. That's often not necessarily useful in computation because there's different approaches, but in terms of derivations, it's very often useful to factor out a constant. So here, we factor out this constant, we put it on the outside, and note that these big N's now cancel, and we're left with 1 over this little n, and then we have our formula for the sample mean here. But why would we go to all this trouble? Well, if we don't have a situation where every individual's got a pi, whatever that happens to be, probability of inclusion, but people differ, then we wouldn't factor this out, but we would leave it in, and this basically then gives us a way to, kind of using the same logic as our expected value up here, to kind of fix the sample mean so that it's now a proper estimator of the population mean. I want to make one more note in passing, by the way, before we talk about the variance. So, and one more thing, if you want to, you can try to calculate the sample mean for the data set given above. I'll let you try that on your own. There's an answer given here in footnote 2. You can see the answer down here, but see if you can try that on your own. So I wanted to make one more note here before we move on, which is, what do we do if we have a nominal variable or if we have an ordinal variable? So means don't make sense for nominal variables such as race, and they should be taken with a large grain of salt for ordinal variables such as a Likert item of how someone feels today. So what do we do when we want to calculate meaningful descriptive statistics? Well, we have 2 alternatives. First, you can just calculate the estimated probability mass function for nominal variables, which is a fancy way of saying you just list the percents of people in the sample who take on each value. We'll discuss probability mass functions in the remainder of this video. So for example, the weighted GSS 2018 has about 72% white respondents, 15% black respondents, and 13% other. Sorry about this crude category, by the way. That's just the way the GSS asked about it on this one variable. You can combine other variables to get better race data, but that doesn't concern us directly here. So that would be one thing that you can do. You can just give those percentages, and that's an alternative to calculating the mean. But note that one other alternative that's very often useful is you could think about these as being three separate binary variables where we mark people as ones if they are members of that group and zeros if not. This is called dummy variable coding. The dummy part isn't meant as pejorative, it just means simple. And so then we could consider each of these percentages to be the mean of the variable when we look at that variable. So just to show how that works, for instance, if we're thinking about a variable called white, where we mark people as ones if they are white and zeros if not. And again, the coding scheme doesn't have any kind of value to it. It's convenient to have one indicate the presence of a group and zero the absence of a group membership. If we had the variable black, for instance, it would be reversed. So we would code people as ones if they are black and zero if not, and then the same for the other group. So the mean of the white group would be written like this. We would have the sum, and you've got this 1 over n on the inside, but you could put it on the outside, of all of the individual scores on the white variable. So what would that look like when we actually calculated it? Well, we would have a bunch of people who are ones, and this would be the number of people who are white, and then a bunch of people who are zeros, this would be the number of non-whites. So these zeros don't sum to anything, so we just have n whites. We have the number of white respondents, and so then this just becomes the number of whites over the number of observations. And then note that intuitively this is the proportion of whites in the sample as well. So the mean of one of these binary variables would be also the proportion. So that's a way in which, for this class, you don't need to go to the trouble of doing this dummy coding. You could just calculate the proportion using a simpler function in Excel, for instance. But it is worth noting that the mean of a binary variable is meaningful, and it gives us the proportion of people that have a 1 on that outcome. Okay, finally, let's discuss the variance, our final basic descriptive statistic here. So the variance is a measure of spread or dispersion. You can think about it as the expected difference between a randomly selected observation and its mean, and we define it formally at the population level as the expectation, or the average, at the population level of the squared difference between the random variable y and its mean, mu y. So it's defined this way. This bold-face v is variance. The variance of y is equal to the expectation of y minus mu, the population mean, squared. And you might wonder why we squared the difference, and there's a good reason for this that leads us to a proof of a useful fact about the mean, which is that it's the value for a given set about which all deviations, or distances of the variable from the mean, like distances of different scores on the variable, are not just minimized, but also 0. So what that means is that the expected value of a deviation, so y minus mu, a random variable minus its mean, is actually 0. And I'll show you a quick proof of that. So the expectation operator, this bold-faced e here, is basically an average. So it is also linear, just like the average is a linear function. So the expectation of y minus its mean, mu y, can be split up into the expectation or average of y and the expectation of mu y. So then, by definition, the expectation of y is equal to mu y, and the expectation of mu y is just mu y because the expectation of a constant, or the average of a constant, is just the constant. So then finally we have that the expectation of y minus mu y is equal to mu y minus mu y, which is equal to 0. So in other words, the deviations of a mean, or from a mean, pardon me, sum to 0. So, and this is true in the sample as well, by the way. So this is why we square the variable here, because, or the deviation, pardon me, because otherwise all the means would be, or all the deviations would sum to 0, and we would end up having 0 variance, even when we clearly do have some spread, so that would make it a bad estimator. Okay, I wanted to make one more note here too. So just as we saw above the distinction between the expectation and mu, there's a similar distinction that we can make between the variance operator, boldface v here, And then the actual variance itself is a fixed quantity for a given population, which we'll write with lowercase sigma squared. So this is kind of the same distinction as I mentioned before between the expectation or the variance with this notation as a function or something that produces an outcome, just like the formula for an average produces the outcome. But then mu or sigma squared or the phrase the average are all sort of the outcome. So one of them just calls more attention to the process itself, and then the other is the result. By the way, you might worry about this power of 2 here. So why do we have this power of 2? Well, the reason we do this is pretty simple. The variance is easy to calculate with, but the interpretation is a little bit difficult. It's the expected squared distance of a point from the mean. And so a lot of times what we do in practice is when we're describing data sets, we use the standard deviation, which is written sigma for the population and s in the sample. And again, this lowercase sigma makes the s sound, so that's why we use it. And then the sample variance is just s squared. So the variance is the square of the standard deviation, and the standard deviation is the root of the variance. Standard deviation is more intuitive. It gets rid of the square, which is nice, but the variance is easier to calculate with because we don't have that annoying square root hat, which we often have to take some extra steps to delete, basically. So that's the variance conceptually. The sample variance is also straightforward, but there's this one weird exception. And you might be thinking, gosh, this guy's going pretty deep here. We're hitting a lot of kind of heavy statistical material here, which is true. But I'm going to give you a little bit of a break here. We're not going to worry too much about this particular correction. So this is very much like, this formula here is very much like the population formula for the variance here, with one exception. So let me describe the formula in a little more detail, and then I'll describe the exception. So let's look here at the formula for the sample variance. We basically take the sum of all the squared deviations. So we take, for instance, for some individual, we find their score. Then we subtract from that the mean. We square it, we add it all up, and then we divide by something very close to the sample size. So it's kind of like an average squared deviation. But we have n-1 here. And the reason that we do this is that because we are estimating the sample mean, or we're estimating the mean, I should say. We're not estimating the sample mean, but we're estimating the mean with the we're estimating the population mean with the sample mean. This introduces a little bit of bias into our formula because in general, the points that we have will be closer to the sample mean than they will be to the population mean. There's a reason for that we don't need to get into, but the basic point is that in general, our formula for the variance, if you ignore the -1, would generally speaking understate the true variance. So when we divide by this smaller number here, that makes the entire quantity bigger, right? So if you divide a number by 100, it's smaller than if you divide it by 1, so making it a little less kind of stark. If you divide a number by n-1, it's bigger than if you divide it by n. So in general, our formula is going to understate the variance unless we put in this correction here, which is called the Bessel correction. And then finally, we can just take the root of the whole thing to get the sample standard deviation, which we denote with S. Now, it may be useful at this point to go ahead and try to calculate the variance for our data set above, just to make sure that you understand what's going on here, even though we'll typically let the computer handle this in practice. We are going to begin with what are called regular variable distributions, or that's my term for them. The distinction is widely acknowledged, but sometimes people don't give very clear terms for these things. So at the risk of introducing more jargon, I'm going to say that regular variable distributions are distributions of variables that we care about in themselves because we're interested in those properties. So a regular variable distribution might be something like the distribution of education or income or something like that. We're going to counterpose that to sampling distributions. Sampling distributions are of interest to us for inferential reasons. So they're distributions of things such as the sample mean across all possible samples or the sample regression slope across all possible samples. These are really nice. They have nice properties. They're the result of a surprisingly beautiful theorem known as the central limit theorem. but they're not directly interesting in and of themselves, except as kind of a curiosity, unless we could use them for inference. Now, this distinction is very strong. In one respect, it's not really a mathematical distinction in the sense that both of these are distributions, these regular variable distributions and sampling distributions, and they both have certain parameters that characterize them, such as their mean and their variance. And sometimes you have regular variable distributions that are approximately normal. Sometimes you have sampling distributions that are approximately normal, where normal means a special type of curve, the bell curve or the Gaussian curve. And from a mathematical perspective, as long as we know the mean and the variance, we're good. They're more or less the same. But from a perspective of people that are learning these things for the first time, it's extremely important to keep in mind that they characterize very different sorts of things. One, regular variable distributions, characterizes variables that we directly care about, sociological variables in our case. The other type characterizes the behavior of sample statistics across many possible samples, which is of less direct interest, but is still very important mathematically. So let's begin with regular variable distributions. These are the distributions that we typically directly care about. So there's a couple of ways to examine an individual distribution for discrete variables, and we're going to focus right now on discrete variables, although we'll turn to continuous variables in a moment. So the first is the cumulative distribution function, or CDF, and you can see an example of that on the left here. We'll come back to it in a moment, but just so you can see what we're talking about. This plots on the x-axis possible values of the variable, and on the y-axis the cumulative percent or probability of data observed up until that value. So you can think about it as percent or probability on the y-axis. Remember that probability can be defined as simply long-run percentages. So in other words, the probability of flipping a heads on a fair die is 50% or 0.5. And one way to think about that is that what that means is if we could flip a fair coin an infinite number of times, the percent of heads would be about 50%. So percent and probability can typically be conflated with one another with no real problems. So if you have trouble with probability, just think percent in the long run. So a CDF makes sense for both continuous and discrete random variables. We're going to look here at the case of discrete random variables. So the height of this function is the percent of observations that are going to be less than or equal to some value of the variable. And we denote this with big F of x is equal to the probability that big X, which is the random variable, is less than or equal to some specific value of x, which is little x. So let's look at this example here. This is a sample cumulative distribution function on the left here for the number of children from the 2018 GSS. So these hollow circles here mean that there's not actually anything observed at that point. So we look here at these red circles because this is kind of a step function. So we've got these jumps, which is characteristic of discrete random variables. I guess I probably should have characterized the distribution first, then mentioned the technicalities. So let's start with how we would read this. So we see, first of all, that the percent of people that had 0 children on the 2018 GSS was about 0.28 or something like that, or 28%. For people that had 1 or 0 children, it was about 0.43 or 4, something like that. For people with 2 or fewer children, it was about 70%. People that had 3 or fewer children, about 85%. People that had 4 or fewer children, about 92%, and so on. So note a couple of things about this function. First of all, these heights, right, represent the percent of people that had that many of that observation or fewer. So it's cumulative, hence cumulative distribution function. Or you can look on the y-axis here and see that this is the probability that the number of children were less than or equal to that value of x. So note also that this means that the function is monotonic, meaning that it's always increasing or at least staying the same. It's never going down, which makes sense, right? So if, in this case, about 70% of people had 2 children or fewer, it's not possible for the number of people that had 3 children or fewer to be smaller than 70%. At most, it would be exactly 70%, in which case that would mean that 0% of people had 3 children exactly. One other thing to note, as I alluded to before, is that we've got these jumps here, right? So note that, for instance, there's a hollow circle right at 1, and that's because we have to skip ahead here to the number of people that have 1 child exactly when we jump up here, or 1 child or fewer, pardon me. And so that's why this red circle is filled in here. The flatness right here is sort of artificial. You could leave this out. It's actually just conventional to include it because there's not actually the possibility of observing any number between 1 and 2 children in this way of conceiving children, and that's probably really the only meaningful way to conceive it. So that's why the line is perfectly flat here. There's no one that has a number of children between 1 and 2, so the function doesn't increase at all. So effectively, you could plot this function by just having these red dots all right here, and this is just sort of the conventional way to do it. Now let's talk about another alternative, which is closely related. It's called the probability mass function, and this is basically just a histogram. In a sample, when you are estimating the probability mass function, it's literally just the histogram in the sample. But it may be worth remembering what histograms do. So unlike cumulative distribution functions, probability mass functions don't need to be monotonic. They can go up and down, and the reason for that is that they plot on the y-axis the probability of having exactly that number of children. So note that right here, the value for the probability mass function of exactly 0 children is exactly equal to the same as the CDF, because at this point, the exact probability of having 0 children, about 0.28% in the, or 28% in the sample, is the first value of the variable, so that's got to be the same as the cumulative distribution function. But then note that the value for 1 child is about 0.15 or 15%. That means there was a 15% chance of having exactly 1 child. So if you sum those two things together, right, 0.28 plus about 0.15, note that what you'll get is about 43%, and note that that was what we got here for the cumulative distribution function. So this function here shows on the y-axis, or on the height, the probability of having exactly that number of observations, that value of the variable, or that number of children, whereas the cumulative distribution function adds up basically all of the heights of the histogram up until that point. So here, between these two, we've got 43% of the sample. Then if we add another one here, this is about, 0.28 or something like that, right? So that should be something in the realm, right? If we've got 43% here, and then we're adding about 0.28 to it, something like that, that means if you do a quick bit of mental math, you should see something about like 65% or something like that. And that's a little bit different to this here, but that's because I'm estimating maybe this is closer to 0.29, something like that. But you can see that these heights are effectively adding up right here, and maybe this is closer to 0.16. But so at any rate, the probability mass function is basically just a histogram. It shows on the y-axis the probability of observing that specific value of the variable. So those are cumulative distribution functions and probability mass functions. So now let's turn and talk about more or less the same thing, but for continuous variables. And so for continuous variables, we do need to make a slight change when it comes to the probability mass function. It becomes a density function, but we can look briefly at cumulative distribution functions, which work actually more or less the same exact way. I wanted to say before we talk about probability mass functions, or cumulative distribution functions for continuous variables, why it is that probability mass functions don't work. So note here on this graph above, when we've got this discrete variable which can only take on a specific fixed set of values, even if that set is in principle infinite, so technically speaking, in a certain sense, the number of children could be infinite. Maybe not the number of children for a particular person, but let's say the number of children who have ever lived. It's clear that there's not an upper bound on that. But again, keep in mind that it's discrete, which means that it can't take on values within certain fixed spaced values. So those fixed space values are the natural numbers, actually technically the whole numbers, 0 through infinity. But we can't have half a child. So again, you can kind of use our basic intuition for when a variable is discrete from before, which is this: if someone tells you one specific value of the variable, you can come up with the next value of the variable no matter what. So even if they come in halves, for instance, like let's say you're thinking about, or quarters. So let's say you're just thinking about a simple example like quarters played in an American football game. So there's 4 quarters, but we don't have fewer than 1 quarter, right? Or one way to think about it is you could measure them on the scale of parts of a game. So you'd have 0.25 of a game, 0.5 of a game, etc. But because those are the smallest increments in which we measure parts of an NFL game, apart from minutes, then that's really all that you can say, right? You just have these fixed sizes, so you'll never have a quarter of a quarter, right? Again, you could measure it in minutes, but then that's a different variable. So you don't have to have these, they don't always have to be whole numbers, but they have fixed increments where you always know what the next value of the variable is. Okay, so that's different with continuous variables because, as mentioned before, if you could have, say any value of the variable, in principle the only limit is measurement, then what that means is you actually don't really have a way to assign probabilities to any particular value of the variable. Technically speaking, they're all probability 0. And that might sound kind of crazy because how can you say that the probability of getting some specific height is 0? Well, if that's not intuitive, think about the probability of any exact value. Say you could, in theory, if you measured it far enough, maybe someone's height is pi, right? That's somewhat unrealistic, but it's possible, right? If you could, in principle, keep measuring to further and further decimal places, which you could, there's not really any limit there. So this might be surprising. So what I want you to think about is if the probability of someone's height being pi exactly isn't 0, it's got to be really, really, really small, right? And maybe so small that, yeah, it effectively is equal to 0. And that's really the reasoning. It's not that we can just immediately say that the probability is 0, but when you work out what's happening, it's basically a limit that becomes 0. So what that means is that probability mass functions don't make sense for continuous variables. I'll show you that in a second, but what I want you to note first is that, once again, in any actual sample, you always have discrete data. So you don't ever observe an infinite number of possible values. That's something that you could conceptually think is true, but you don't actually observe that because you can't observe infinite data. So a variable can have a probability density function if it's continuous, but any data set of realizations cannot. We just have an estimate of the probability density function, which ends up being a probability mass function. So for example, here is the empirical cumulative distribution function and probability mass function of height from the 2017 to 2018 NHANES, which is like the big government study of health outcomes in the United States. So height is a continuous variable, and it can take on many possible values in the sample. So note that these look pretty smooth, right? This cumulative distribution function in particular looks almost exactly smooth. You can see if you zoom in that there are these little kinks, and that's not a pixelation problem. That you can see the quality is quite good. The other lines here are solid, so this pixelation is actually a result of the fact that we don't observe infinite possible values, just very, very many. And the same is true here for this histogram. This histogram looks almost smooth, but it's not quite, and that's because you have a discrete variable here in practice, or what you have are discrete data, I should say. The variable itself is continuous. But the data that we have are discrete, so a cumulative distribution function and a probability mass function also make sense. But if we could somehow observe these variables in their full abstractness, then they would look a little bit different. So the cumulative distribution function will look effectively the same, although it'll always be smoother than it looks for those discrete variables, which are always going to have that kind of step function character, even though if you have very many possible values, it might be somewhat attenuated. But density is going to look a little bit different, and I want to show you in a moment what that looks like. But first, let me describe what density is. So density is a bit of a trickier concept. It just, formally speaking, is probability per unit. Probability density just means, much like density means mass per some physical space, density means probability mass per some unit. It's a rate, right? And so actually density is really just speed of probability. So the probability density function is just a graph of the speed of the cumulative distribution function. So we can look at an example down here. You can see in this particular case that this is the cumulative probability for a normally distributed variable, and here I put in the actual function. So these are not based on any discrete data set. These are in fact based on just the kind of nice smooth functions. So here you can see that this is the cumulative probability for a normally distributed variable, and it's getting progressively more probable as you get closer and closer to 0, and then it's getting, pardon me, here, it's significantly less probable on the tail, and then you can note that the probability is still positive here, but it's increasing very slowly in this other tail. So what that means is that values are progressively more and more likely as you get closer and closer to 0. So the speed here of this function is fastest as you approach 0. And one way to think about that on this density curve is that the area under the curve is much greater as you're closer and closer to 0, and the area under the curve is much less as you get farther and farther from 0. So in fact, this is a graph of probability density. The speeds of this function are fastest closest to 0, which means that the heights, this function on the height here, the height basically means the speed of probability. So here the heights are largest where the speeds are fastest. And you can interpret the area under the curve here as being probability. So you've got probability per unit on the y-axis, and then if you take, say, a bunch of rectangles and approximate the area under the curve, those rectangles would have height of density, which is probability per unit, and then on the x-axis, or the base of the rectangle, you've got units. So the area, you've got probability per unit times unit, and the units cancel, you just end up with probability. So density curves have this interesting fact that the probability here shows up as an area under the curve, not as the heights. So if we come back to the probability mass functions here, these heights are probabilities, or in our empirical estimate of the density curve, these heights are also probabilities, they're percents, but on a true density curve, the probabilities are actually areas under the curve. The height is a density, which is hard to interpret, and also it doesn't really matter that much because how do we locate some exact point here, right? And that ends up being impossible because if a value, if this is a truly smooth continuous line here, no actual value that we could observe is really locatable here because in theory it could take on an infinite number of decimals, right? So it's kind of meaningless to talk about specific values of the variable. What we're instead interested in is the probability of a range, or that's something that we can talk meaningfully about, and that we can just figure out by looking at the area under the curve between those 2 points. So these are the standard normal cumulative distribution function, probability density function, and these are how any normally distributed variable, once we take a standard score, is distributed. And a standard score is just, we subtract off the mean of that particular variable, we divide out by the standard deviation of that particular variable, and then any normally distributed variable will have this specific distribution once it's standardized. The reason that we do that, by the way, is because of this important fact above, and I probably should have put this in a slightly different order, which is that even though probability density functions don't actually characterize any variables that we can actually observe, they characterize the theoretical distribution of things such as sampling distributions, or their sampling statistics more exactly. So sampling distributions are probability density functions, or they can be represented that way. And so we can use them to model these important distributions of the behavior of sample statistics across many samples. And as mentioned before in this class, it turns out that the random variable y bar, or the sample mean, is continuous. It can take on any number of values, and it's normally distributed even if the distribution of the random variable y is far from normal. So here, I went ahead, and I've shown you this before, but I simulated the sampling distribution for a bunch of sample means from this population distribution of Mother's Education, which is in pink. Note that Mother's Education is not actually normal. It's not really got any recognizable shape. It's got a skew, and it's got multiple modes here, which are kind of arbitrary. So you've got 2 modes here, then a fall off, then a mode here, then a fall off, then a mode here, which just represents the actual distribution of education. It's just kind of strange like that. Not strange, but just arbitrary. But note that the distribution of sample means of Mother's Education is very close to normal. And this isn't an actual probability density function because this is a simulation. So I took 5,000 sample means, which is a large number, but it's not infinite. So you do actually see here this kind of discrete quality to it. It's not smooth, but this is getting really close to a continuous distribution because 5,000 is not actually close to infinity, obviously, but from a human perspective, this looks pretty close to continuous. But theory tells us, and you can also see that the simulation clearly points in the direction of this being a nice smooth curve here. So this is this very nice smooth curve. And that's basically why we care about these continuous distributions, is because we know that the sampling distribution of sample means, if we could observe a truly infinite number, would be smooth and continuous and normal like this. And we don't actually need to observe that infinite number because we can prove with theory, there's a very nice logical proof that it is in fact smooth like this. Now I want you to note that it's quite difficult to take areas under the curve of the normal by hand with calculus, but it's easy to do with a computer or a table. And you can actually, for most purposes, just memorize what number of standard deviations on the x-axis you need to go out in order to get a certain area under the curve. By the way, the x-axis here can be interpreted as a number of standard deviations, and that's because you get this standard normal curve by dividing out by the number of standard deviations on the distribution that you have. So here, basically what this represents, this is the distribution of a standard normal variable with mean 0 and standard deviation of 1. But if we wanted to find the number of standard deviations we need to go out on an arbitrary normal curve, we just say, okay, well, on the standard normal, if we go out, say, plus or minus 2 standard deviations, that includes about 95% of the area under the curve. So if we don't have standard deviation of 1 on our variable, we just go out that number of standard deviations to capture that central area. So what are those important numbers of standard deviations that capture certain areas under the curve? Well, these are, in one sense, arbitrary, like there's no special logic to them, but many people just make the choice to memorize some of these key ones. So for instance, if you go out plus or minus 1 standard deviation, you've got about 68% of the area under the curve. Conveniently, going out 2 standard deviations includes 95.45%, and then going out 3 standard deviations includes 99.73%. So these are really nice, especially this middle one here, because 95 is a pretty easy number to interpret. It's most of the area under the curve, but there's still some marginal difference between it and the total area under the curve. And it happens to be associated with this nice number. And in fact, going exactly 1.96 standard deviations is almost exactly 95% of the area under the curve. So if you've ever heard of a 95% confidence interval, which is extremely standard, even if it's technically arbitrary, this is why. So we're going to focus on this here, this 95%. So we'll say that going out plus or minus 1.96 standard deviations on a normal curve includes basically 95% of the area under the curve. And that's an important fact that we'll put to use quite often. So you might already be able to tell where this is going. But what this means basically is that we can use this fact to say something useful and important about the properties of any given sample mean if we know that it comes from a distribution such as this one. So what is it that we actually do with that information? Well, I want you to note 2 things here. First of all, this curve has a lot of nice properties. So if a standardized sample mean is drawn from a curve such as this one, there's a lot that we could, in principle, say about it. On the other hand, if we have an arbitrary underlying population distribution, such as this one from Mother's Education, it's harder to say much specifically about this curve because it's kind of unusual, and this is not the curve, this is not an exact, probability distribution. We can't model it exactly. So if we think about just drawing one person from this distribution, there's kind of a couple of problems here. First of all, we don't know exactly what that distribution looks like. If we just observe a single sample, we don't typically observe the population distribution, so we don't know what it actually looks like. The second is that even if we happen to know that, it might have unwieldy properties that we're not fully able to deal with mathematically. So here's this cool fact. We can think about each person in a sample as a random variable before we select them. So each person, before they make it into our sample, is a random variable. And this is very challenging often at first for people that are new to these ideas. So make sure you kind of get this in your head. Before I actually select a person into the sample, they are a random variable. Their score on a variable, such as income, is also a random variable. So there's kind of this cool fact that although individuals are taken from those unknown and possibly kind of weird population distributions, if we start adding up individuals and they're all independent and they're identically distributed, and that's not exactly true because once we take someone from a population distribution, the population distribution changes a little bit. But if we think about the population being very, very large, which it almost always is, relative to the sample, taking one person out hardly changes it. So if we have these independent, identically distributed random variables, so they don't have anything to do with one another directly and they all come from the same distribution, then when we add them all together and say, look at their total or look at their mean, then they basically are coming from a distribution. Their mean or total comes from a distribution that we know about. It looks like this one here. And it turns out that we can actually also figure out the mean and the variance of this distribution. So we not only know that it's normal, but we can also figure out, or take a pretty good guess at, the mean and the variance of that sampling distribution, which allows us to say a lot about any one sample. And this is a really important fact. So, in fact, I would go so far as to say that this is the reason, the primary reason, that pre-statistics, at least before supercomputers, are even possible. And as I mentioned before in class, Galton has this nice quip, which is that the law would have been personified by the Greeks and deified if they had known of it. So it's so shocking and surprising that Galton thought that the Greeks would have basically formed a cult to it in the way that they formed a cult to other mathematical ideas. As the sampling distribution in a little more detail so that we can do inference on it. So all we need to do in order to do inference is to turn the sampling distribution that we have, which will have a mean and a standard deviation that aren't always going to be the same, into a standard form. And technically this process of converting it to a standard form isn't really necessary with computers, but it's first of all a convenient way to think about what we're doing. We're trying to use these general properties of sampling distributions to say something about the one that we specifically have. And it was necessary before computers. So it's worthwhile to think about the process in the following way. So we want to standardize our sampling distribution. And what we need to do is basically take the actual sample mean that we have and place it on a standardized sampling distribution. So we need to find the standard score of a given sample mean that we have access to, and then we can find the associated areas under the curve. So the easier part of this is to think about the mean. So the sample mean is an unbiased estimator of the population mean. So the sampling distribution is going to have a mean, mu y bar, which is simply equal to the population mean, mu y. So that's the mean of our sampling distribution. It's the true population mean. You might wonder, well, don't we not know the population mean? And that's true. We'll come back to that. Now, the next thing we need to worry about, since that'll be easier to solve, is the standard deviation of the sample mean, which we refer to as the standard error for the sake of distinguishing it from the regular variable standard deviation. It turns out to find the standard deviation, it's easier to find the variance and then take the root. So note that we're after the variance of a sum of independent, identically distributed random variables, which are divided by the constant n. So that's what the sample mean is. There is a really useful general formula for the variance of a sum of random variables that may or may not be related. You can see the appendix here if you're interested. It's useful but also extremely simple for independent random variables. The sum of the variance, the variance of the sum of n independent random variables is just n times their variances, or if they all have the same variance, or it's just the sum of the variances if they're different. So let's let y bar represent the sample mean of a random variable comprised of n independent, identically distributed random variables, y1, y2, yn. Each variable comes from a population distribution with standard deviation sigma y, which we'll refer to using sigma just for simplicity. So here's how we can find the variance of that sum, or really rather the mean, y bar. So the variance of y bar, which we can denote sigma squared y bar is equal to the variance operator applied to the sum from I equal to 1 to n of yi over n. Now, constants factor out of variances as squares. You can look up a proof of that later, but basically if you imagine multiplying every number in your data set by some constant a, the variance is going to be the mean effectively of a yi minus a y bar squared, and then you distribute the square and a squared pops out. You can see a proof of that on the Wikipedia page if you want, but you can just know that constants factor out of variances as squares. So we pull out the n, becomes 1 over n squared, and then we've got the variance of the sum of all these yi's. Now, the variance of a sum of independent, identically distributed random variables is just the sum of that variance times n. So we have here sigma 1 squared plus sigma 2 squared up through sigma n squared, or the variances. And that ends up just being n times the variance. So we have n times the variance over n squared, and these cancel, and we have the variance over n, which is the variance of the sampling distribution. Or if we want to convert it to a standard deviation, we just take the root of the whole thing. So the top becomes the standard deviation, which is the root of the variance, and the bottom becomes square root n. So this is maybe the more common expression. If you look up standard error of the mean, you'll see that this is the standard error of the mean. By the way, we can connect this to our earlier abstract discussion of total survey error. So we said that the following equation held that the mean squared error was equal to the sampling variance plus the bias. And if we don't have any bias, as we don't in this particular scenario, when we use a simple random sample and a mean from it to estimate the population mean, there's no bias. So then we just have the sampling variance as the source of error, and this here is the sampling variance for the mean. So we've given the sampling variance in some more detail here. Okay, so now we have the variance and the mean of our sampling distribution. We want to do inference on the population mean, but we don't know actually the population mean, so we don't actually know where the sampling distribution is located. So how can we use our formula? What can we do with this information? First, we can simply recognize that about 68% of sample means will fall within plus or minus 2 standard deviations, sorry, that should be 1, of the true population mean. I'll fix that. So we could simply add and subtract 1 standard error, or the standard deviation of a sampling distribution, to our sample mean to have a 68% chance of having that true mean mu y in there. It's a little more conventional to have a higher level of confidence and add and subtract 1.96 standard errors to our sample mean to have a 95% chance of including mu y. The general formula for a confidence interval you can generalize. So with confidence level C, confidence with interval with level C is y bar plus or minus whatever z-score, or number of standard deviations within which C% of the area under the curve lies, plus, the standard error, sigma over root n. For the sake of our class, I don't want you to calculate other kinds of confidence intervals because it just adds an unnecessary layer of calculation and potentially confusion. So just use a 95% confidence interval. So here, Z95 is equal to plus or minus negative 1.96, or you can use 99, so that's plus or minus 2.56 here. I think I said negative before, but I meant to say plus or minus 1.96. So you can just use one of those two, and those will include 95 and 99% of the area under the curve. So below is a picture of why this works. So suppose that we have population level data on mother's education. We know that the true population mean mu is here. It's centered at 11.8 or 9, something like that. And when we take 5 random sample means, and then we calculate those confidence intervals, note that although no sample mean is identical to the population mean or to one another, all 5 sample means within their with their confidence intervals, which are plotted here, include the true population mean. Now we don't know where, like let's just say we had one of these samples and we don't know the true population mean. We don't know where the true population mean is in the confidence interval. It could be to the left of our mean or to the right of our mean, meaning smaller or greater. But we know that there's a 95% chance that it's going to be somewhere in that interval. So that's the logic, right? Is because within plus or minus about 2 standard deviations of the true mean, 95% of the sample means will fall. If we add and subtract 2 standard deviations to the sample mean, we have a 95% chance of including the true population mean somewhere in there. And all we need to know is the standard deviation of this sampling distribution, which we derived above. It's sigma over root n, and the number of standard deviations that include 95% of the area under the curve, which is 1.96. So that's the logic of why a confidence interval works, and you can just know that when you calculate this formula here, it is going to work 95% of the time to include the true population mean. Now, sometimes it won't. I didn't show an example here, but you might see a sample mean right over here, let's say, and add and subtract it, and then you won't include the true population mean, but in the long run, this should only occur 5% of the time. So let's do a little bit of practice. So suppose I have a sample in which the mean of the respondents' ages is 35, and I want to come up with a plausible range of values for the population mean age. Let's suppose that n is 900, I picked a perfect square just for convenience, and I happen to know that the population standard deviation is 3. What are the boundaries of a 95% confidence interval? So what we would do here, we can skip down to the answer and I'll show you, is we first write our sample, we can write out the formula first if you want. So we write out our sample mean first, and then we add and subtract the number of standard deviations that include 95% of the area under the curve, which is 1.96, times the population standard deviation 3 over the root of the sample size. Sample size is 900, the root of it is 30, so 3 over 30 is 0.1, and 0.1 times 1.96 is 0.196. So then we just do arithmetic. 35 plus or minus 0.196 is equal to 35.8 and 35.19. So we would say with 95% confidence, we believe that the true population mean age is between 35.8 and 35.19. I'm sorry, I flipped the order of these, not that it really matters, but 35.19 and 35.8. Okay, so that's why the confidence interval works, and that's how we would calculate it. Our second technique is a statistical test, and this works for fundamentally the same reason as a confidence interval, and they're functionally the same for means. For other kinds of statistics, there will be one reason to prefer the confidence interval or the test, but you can use one or the other depending on the circumstance. So this kind of now comes to the problem that we mentioned before, that we don't know the population mean. We saw before that, well, that's the whole point of statistics, and so a confidence interval, we just add and subtract a couple of standard errors, and we know that that'll have a pretty good chance of including the true population mean somewhere in there. But what if we wanted to, say, test a particular value of the population mean? So let's say that someone tells us that they believe that the population mean age is, say, 40 or something like that. How could we test that? Well, here, we actually don't need to guess at the population mean because we are stipulating one. We're saying that we believe the population mean to be some value. So this actually gives us an anchor or a location for the sampling distribution. So we can picture the sampling distribution under a null hypothesis that the true mean is equal to some value mu naught. And then we can calculate the standard score as if that were true and find the associated probability. So if that p-value or probability is small, say less than 0.05, we reject the null hypothesis. And finally, the level at which we reject the null, known as alpha, is arbitrary, but a conventional cutoff is 0.05, which happens to match the 95% confidence interval in theory, basically. And it's conventional to take the p-value, not just of the statistic we got. So let's say that this is our sampling distribution under the null, and we observe this particular sample statistic. One probability, or a one-sided probability, would be the probability of observing a sample statistic this large this small or smaller, so here to here, but also to find the converse as well, or basically the probability of the additive inverse, so this thing times -1, which is this thing here, find the probability of that, or larger. So that's a two-sided p-value. And what this tells us is, under the null hypothesis, this is the probability of observing a sample statistic this far away from the mean or more. In this example below, again, we're supposing that we know the true population parameter. This is meant to show you what happens when the null hypothesis is true. So sample means are quite rarely more than plus or minus about 2 standard deviations away from the mean. But you can see that occasionally in this particular sample set of 5 samples I did, there was actually one sample that was more than 2 standard deviations away from the mean. It's this one here in the darkest red. You can see that the probability of a sample statistic this small or smaller plus 1 correspondingly larger is only 3%. And so we would reject the null hypothesis for this particular sample statistic here. What this tells us is that when we don't know the null, we can just, when we don't know the true value of the mean, we can just assign it the value of the null, and then we would say, well, we'll only see sample means about 2 standard deviations away from it, if it's true, about 5% of the time. So if we observe a sample mean that is that far or farther, we can reject the null because we would only see a sample mean that far away or farther about 5% of the time under the null hypothesis. So this is the second technique, and this is known as hypothesis testing. So let's again do a little bit of practice. Go back to the example before in which I have a sample in which the mean of respondents' ages is 35, and I want to test the claim that the mean of age is 35.5. So how should I do this? Well, first I calculate my raw difference between the observed mean and the hypothetical mean, which happens, and this should be 35.5 by the way, which happens to be negative 0.5. Then I calculate the standard error, 3 over root 900, which we already did, which happens to be 0.1. And then finally, I find the test statistic by dividing negative 0.5 by 1, or 0.1, pardon me, which is negative 5. Then finally, I look up the p-value for this statistic and the additive inverse, which is 5. I'll show how to do this with code in class. This is so small that it would not be visible on a picture of the sampling distribution, so the probability, sorry for the code error here, of any standardized sample statistics absolute value being larger than this is very, very small. It's a probability that's, much smaller than 1% or even 1/10,000th of a percent. So since this sample would be extremely improbable under the null hypothesis, we reject the null hypothesis. So basically, we can just standardize our test statistic. This gives us a standard score that comes from the standard normal distribution, and then we can find the associated probability and compare that to some cutoff. We don't always even need a cutoff here by any conventional standard. This is way too improbable to be a freak coincidence. We would say that this means that the null is probably false. Finally, I just want to add one more complication, and this is where the lecture will wrap up. In practice, we don't know sigma. We don't know the population standard deviation, just like we don't know mu, the population mean. So we estimate it with the sample standard deviation S. This causes some additional uncertainty on our estimate, and it's now taken from a distribution that is close to normal, but it's farther from normal the farther the sample size. This distribution is known as the t-distribution. Many statistical textbooks get really excited about this. You can tell that I'm a bit of a geek and I find this stuff really interesting, but I happen to find this particular part of sample statistics really not that fascinating. A lot of people do for reasons that I'm not totally clear on. And one thing to note is that for any large sample size, this effectively makes no difference whatsoever. So for the non-mathematician, pardon me, sorry, it's been a long lecture, I think this is kind of a boring technical detail. So I'll simply say that this means you should look up your values for the test and the confidence interval in a t-table, not a z-table, but the basic meaning of a confidence interval or a p-value is the same. If you're in my SOC257 class and you're watching this, I'll show you how to do this in Google Sheets during our lab, so don't worry too much for now. It changes our procedure, but only slightly. So thanks for watching. This has been an introduction to basic descriptive statistics and basic inferential statistics.